Got it. I think he's ready.
Hello everyone. Welcome to ECE 590 seminar. Today we welcome Khaled, the Mohammed Alshehri. I hope I say your
Yeah, you
names
did
right.
it.
He's a PhD candidate at the Department of Electrical and Computer Engineering in our school, and he's primarily interested in applying control and game theoretic methods in power and energy system. And today he will talk about the electricity markets.
Yeah, thank you,
Yeah.
Fu. So I'm Khaled. I'm from the control group at CSL. And in a nutshell, what this says, cascaded options for wholesale electricity markets. In a nutshell, this is about coming up with a centralized mechanism to mitigate the volatility due to uncertainty coming from renewable supply. So you can't hear me? Can you hear me all? All right. So is it working? Yeah. So the premise of this work is energy is typically procured in advance to meet demand requirements. And once you have renewable supply, you introduce uncertainty, intermittency, and non-dispatchability, non-controllability. So what this means to us in this talk is you would have an increase in your forecast errors because you do procurement in advance. You have some predictions. These predictions have some errors. These errors increase significantly due to renewable supply. What we do in this work is to come up with a centralized mechanism to mitigate the effect of that in terms of payments. So, and how do we do this? Is by introducing a financial derivative, which is a cascade call option. So I'll talk about that. And this is what this talk is about. So again, high integration of renewable supply introduces uncertainty. This uncertainty has a reflect in the payments. These payments will be volatile because of your errors and this uncertainty, and we try to mitigate that. So this is the essence of this work. So as a benchmark, we have a dispatch model and a payment scheme. So for the dispatch, here we talk about a certainty equivalent dispatch. So what this means is that you would have some random variables in the system, and you would have forecast in these random variables. And given these forecasts, you would do your optimization for the market. So you would forecast on certain variables and dispatch against these forecasts. And if you don't have much uncertainty, then your errors will be small. But if you introduce much renewables, then these errors will increase. And we try to mitigate the effect of that. And you would have, in parallel to that, a payment scheme. So in this work, what we do is we abstract the market into two stages, a day-ahead stage and a real-time stage. And we will have day-ahead payments and real-time payments with different prices. Is it clear so far what we're trying to do? Yeah. So let me go. As an outline, I'll illustrate some of the financial risks with on a benchmark example, and that is stylized. And then I'll show how can a bilateral trade between two market participants mitigate these risks. And these risks come from the uncertainty due to renewable supply. Then we'll try to generalize that and come up with a centralized model to mitigate these risks. So the bilateral case here is just to motivate the idea of coming up with a centralized model. Then I'll talk about some generalizations, challenges, and I'll model risk aversion as time permits. So as a benchmark example, this is a very stylized example. but it reveals the things we're interested in this work. For example, we have we have a peaker plant and a base load generator and a renewable supplier and fixed demand. So we abstract many details and come up with this stylized example to reveal the properties we're seeking and interested in, and to show. So this is really just to show a point, and we apply our model to that and see the properties that we're seeking. So let's say the renewable supplier has some uniform distribution of supply. So this is in real time. So the model.
The word available is problematic there.
What's that?
The word available has a certain meaning in power systems.
Okay.
So it's problematic over there.
Problematic. Okay. So the.
What do you mean by that?
So I mean the realized one. So this is a set of scenarios at which we have a probability distribution, right? And these are the possibilities of available wind tomorrow. This is what I mean.
Nobody knows that. In other words, we don't have distributions because we can give you on average what the data is, but we don't have distributions.
Yeah,
I mean, it's not analytic distributions.
Of course, it's not analytic, but what I'm saying is this is a stylized example to reveal some properties in the system that reflects what happens, and it motivates it to come up with our model. So it's a stylized.
When we talk about available, we mean is the generation on when needed, or is it on outage? That's what the word available means in power systems.
Okay, thanks. All right. So for this stylized model, we have a uniform distribution. And X omega would reflect in this stylized case what the possible wind that we might have tomorrow. The possible amount of wind we gather. We let the cost to be 0. So really, and also we consider a benchmark market at which you have a day-ahead stage and a real-time stage. So this is a real-time. This is the variable real-time. So real-time, we will have some upper bound on how much wind you can use. And we don't know that yet. But we assume it has some uniform distribution. And we would have a base load generator. Again, these constraints are not 100% realistic. They are very stylized to reveal the things that we are interested in for this work. We assume what this says is that the base load generator cannot alter the generation from the forward stage and the real-time stage. And we assume the cost to be a unit cost per unit cost. Then we have a peaker power plant that is more expensive than the base load generator. And in this case, the peaker plant will make up the difference between the realized wind and the demand. So it has infinite capacity. It is very fast. You assume that in real time you can produce as much as you want in this stylized example. And it has cost rho strictly greater than 1. This is to reflect that it is more expensive than the base load generator. Is it clear so far? All right. So if I do a certainty equivalent dispatch, what will I do is I will see some XR. This is the wind to be produced. And the upper bound here is mu, which is the expectation, which is the mean of the random variable that we had. So I don't know how much wind I will have tomorrow. So I will replace that random variable with its expectation and optimize given that number. And I minimize the cost of the system. This is the production cost, and this is the supply balance constraint. And I will have a forward price that will be the Lagrange multiplier of this constraint. Call it P star. And in this case, it will be 1. The reason is because if I expect the wind to generate up to mu, then I will use that, and for whatever is left between D and mu, I will use the base load generator to produce that. So XB star is D minus mu, and I will not use the peaker plant. But then tomorrow, real time, if the realized wind is less than that, then I will activate this. So what happens is in this model, what you do is you look at, you given the realization in real time, you would optimize again. And what will change is this upper bound, the available wind at that moment. So if I write that again, so I'll minimize the total cost subject to the same constraints, and I will have this replaced. I'll have mu replaced here. So the real time market clearance, oh, this is unexpected. Yeah, it is Windows. I had it on Mac. Yeah. So what this says is the base load generators dispatch is unchanged, and the peaker plant's dispatch is mu minus. Can I use my laptop? Because I'll have a bunch of these. Can I use my laptop connected? Because yeah, I think I would want to do that. Yeah. So because I have a bunch of these equations, and like if I don't know what these characters are. Yeah, I can. I think I have it here. Yeah. I have HDMI and VGA too. Yeah. Yeah.
What does the bar mean above value?
Which bar? This is the upper bound.
But why is it the function of omega? Omega, I thought, is just a sample.
Yeah. So, given omega a realization,
Yeah.
I will have an available amount of wind, right? That's it. So this is the maximum available wind. Given that.
Are you talking about stochastic process there, or are you talking about random variables?
So it is a stochastic problem, but this is one way to solve it by replacing all your random variables with their certainty equivalence, and then you optimize over them. Then in real time, given the realization, now you know, now you don't have, it's deterministic now. So it's a deterministic way. It's
in a sample space. I don't understand that every sample has a different upper bound. That's the element I'm not clear about.
So the upper bound is the available wind, right? So you want to use as much.
It doesn't mean, when you say available wind, it doesn't have any meaning in the power system.